So I've previously covered chapter 10.1, which is relationships between heat and work. Now we're on to the first law of thermodynamics. You might remember from the chapter where I introduced energy that I discussed a frictionless roller coaster where mechanical energy is conserved. In real life, however, there will always be some friction that's limiting the motion of this roller coaster car, and thus, as the roller coaster car moves, some of its energy will be converted to internal energy. However, it's important to note that the energy of the entire environment, so not just the roller coaster but also the track, will remain constant. The first law of thermodynamics takes into account these changes in internal energy, as well as work and heat. It states that the change in internal energy, or delta U, is equal to the final U minus initial U. This also means that the change in internal energy is equal to Q, which is the energy transferred to the system as heat, minus W, which is the energy expelled from the system as it does work. And when we're looking at this equation, it's going to be very important to keep the signs of these variables straight, depending on exactly what the system is doing. So, for this energy as heat, we'll express Q as being greater than 0 if energy is added, so it's increasing, and less than 0 if energy is lost as heat. Then for W, for work, it'll be greater than 0 if work is done by the system, because as you can see, if W is positive, this will be subtracting, so it'll be a negative value, work done. And if work is done on the system, W will be less than 0, turning this into addition, and that will mean that the energy of the system is increasing. A process where a system returns to the exact same conditions under which it started is known as a cyclic process. This means that the net change in energy, or delta U net, will equal 0. And then we know that delta U equals Q minus W, so we'll plug this in over here, we'll make that equal to 0. And now if we add W to both sides, we get that the Q net must equal W net. In other words, the same amount of energy that's added to the system is lost as work. That's what makes the process cyclic. So now we're going to practice the first law of thermodynamics. Number 1. Heat is added to a system as the system does 26 joules of work. If the internal energy increases by 7 joules, how much heat was added? So we have our equation where delta U is equal to Q minus W. We know our delta U because it says that the energy increases by 7 joules, so that'll be a positive 7. That's equal to Q, which is what we're solving for because we're looking for the heat that's added, minus, and then we see that the work is done by the system, so we'll be subtracting this work. That's 26 joules. Now if I add 26 to both sides, we get that Q, or the amount of heat added, is equal to 33 joules. Number 2. The internal energy of gas in an engine decreases by 195 joules. If the gas does 52 joules of work, how much energy is transferred as heat? So once again, we know the amount that the internal energy changes, and we know how much work is done, and we're solving for heat. So this time, the internal energy decreases, so we'll call this negative 195. That will be equal to Q, whatever this is, and then we'll be subtracting work again because it's done by the system. So minus 52. Now, if I add 52 to both sides, I get that Q, or the energy transferred as heat, is equal to negative 143 joules. This means that 143 joules are lost as heat. Number 3. The internal energy of a gas is increased by 560 joules. If the gas absorbs 240 joules of heat, how much work was done on the gas? So we know delta U, that's equal to Q minus W. And we also know that the internal energy was increased by 560 joules, so that's positive 560. That would be delta U. Now, Q is the amount that's absorbed as heat, so that's 240, and we know it's positive because that's heat that's taken in, or it's added. And then we're solving for work. Now we'll subtract 240 from both sides. And I get that work is equal to negative 320 joules. Now this negative just means that the work was done on the gas rather than by the gas. And since we already know it's done on the gas in the problem statement, we can just express this quantity of work as 320 joules. That's just the magnitude of the work.